You have a chair? Very nice to meet you. Yeah. Nice meeting you.
Right. Hi, good evening, everybody. Welcome to Soapbox. My name's John Durant. I'm the director of the MIT Museum, and it's great to see another excellent crowd here for the third in our series of what seem to now be called salon-style conversations about science and technology. I think the salon style means two things. One is you may have to stand, and the second thing is you'll be offered a glass of wine. So it's called swings and roundabouts. Anyway, we're delighted to be here back again, once again, with I'm sure you'll agree, an intriguing subject and a superb presenter. I want to say a couple of words about how the evening is organized. That's for the benefit of any of you who've not been to one of these before, and then we'll get straight into it. The idea is that we give as much of the evening as we can to, I think, what people like to call intelligent conversation between you and our speaker about the subject of the evening. And the way we organize that is that we ask our speaker to present for 15, 20 minutes, not much more, and to be as provocative as they like. And then we're going to invite all of you to spontaneously self-assemble into small groups for a few minutes and discuss what you've heard and agree what, for you as a group, are hopefully the small number of most interesting or relevant issues that you'd like to discuss. Questions, themes, whatever, but keep the number small, because otherwise we won't get a chance to deal with all these things. And they'll be fed back, and my colleague John Bijur, who is here somewhere, but I can't see him, hello, he's going to type those all into a word processor so that we can see the questions, and we'll use your comments, questions, issues as the agenda for the rest of the evening's conversation. It's really as simple as that. If the numbers here mean that some people just can't see and participate effectively here, then we may have people over in the large conference theatre behind, and they can contribute their questions as well and see what's going on a screen. I think that's really all. Was there anything else I was supposed to say? Good. John will wander around when we get into discussion as well, handing out a microphone for those of you who want to make comments or ask questions. Now, for this evening's talk, we're very lucky to have Professor Donald Sadoway here. He's from the Materials Science and Engineering Department. I'm sure most of you will have seen the article about him and his work that appeared in the Globe earlier this week. I was told when we first it was first suggested to us that we must have Don Sadoway in this series, that he was going to come and tell us how we were going to manage to live without oil or dependency on oil in the future. And now that President Bush says that's what we've all got to do, it seems even more relevant than it was before the State of the Union address. I'll leave it, though, to him to say just exactly what he really means, so I won't confuse you with what I have to say anymore. I'm really pleased and grateful that Professor Don Sadoway is with us this evening. Over to you.
Well, thank you. It's a pleasure to be here, and thank you for coming. You have nothing else to do on a Tuesday night here in Boston. Okay, so I was asked to talk about energy and sustainability and the path to sane, and I'm going to do that. I'm going to do that in a very short period of time. I'm going to take no more than 15 minutes so that we can have a lot of back and forth. But I think that the first thing we need to do is to change our perspective about this. I think there are a lot of deep-seated preconceived notions about what's doable and what isn't. So I'd like to begin by telling a story. The story goes, there's a woman here in Boston who's got a sister out in the West Coast, California, and the sister is dying. And so the woman from Boston decides to visit her sister in California. She's never been to California before, but her sister's dying and she's got to go to California. So she goes to California. She spends 2 weeks in California. She spends time with her sister, and there's a lot of difficult conversations that take place, but she makes peace with her sister and returns to Boston. And her friends ask her, what was it like in California? She said, it was terrible. It was terrible. He said, why? What was bad? She said, the climate? No, the climate was terrific. He said, well, was it the people? Were the people unfriendly? No, people were terrific. He said, well, was it the food? No, the food was fantastic. Well, what was so terrible? She says, it's so far from the ocean. Because the ocean is to the east. So I want you to start thinking about, your preconceived notions. See, you're way ahead of this, all right? That's just, so let's imagine a world in which propulsion, human propulsion, does not involve the use of carbon. Let's imagine that. And then let's imagine what it would take to get to there from here. So what would that world be like? It would be an electric world. It would be clean. It would be virtually inexhaustible. It would be silent. But it would not be a world of hydrogen-powered fuel cells. It wouldn't. And, this is not my approach to knocking on the current administration. I'm talking science policy here. So I don't care who's in the White House. I'm talking about the wisdom of a hydrogen economy. So I want to get that out there and set that aside. I'm talking about the energetics of hydrogen and propulsion and so on. So let's think about that for a second. So what does that involve? Let's look at some history. When I teach my freshman chemistry class, I usually begin a brand new unit with a history lesson. We go back and we look at the people that were involved at the inception. So where do fuel cells begin? They began in 1839 in the UK. William Grove, born in Swansea in Wales, went to school at Oxford. And he invented this device which he referred to as the gaseous voltaic battery. The gaseous voltaic battery. The term fuel cell didn't come until probably the dawn of the 20th century. And it involved consumption of gaseous feedstock to cross an ion selective membrane and converted this chemical energy into electrical energy. That was 1839. To this day, what are the commercial applications of that technology? It's not because people are not working hard. It's not because people aren't smart who work on fuel cells. There's a cost issue associated with it. So let's look at hydrogen-powered fuel cells from the perspective of cost. Because, there are three answers to technology assessment. One is it doesn't work. That's easy. The second is it works at the lab bench but is economically inviable, and that's a function of time. What was inviable 30 years ago? When I was a youngster, freshman in college, oil was less than $2 a barrel. And I was at the University of Toronto, and people were talking about the Athabasca tar sands in Alberta. And they said, oil would have to be, $18 a barrel before anybody would pay attention to that. And of course, every fool knew that oil was never going to be $18 a barrel. So what was inviable at that time is inevitable today. So I'm talking about today. Niels Bohr said prediction is always difficult, especially when it pertains to the future. So I'm not going to venture about the future. So what are the issues? Why are fuel cells not out there now? So I'm going to give you 4 reasons to think about. And these are, one of the things that people at the MIT Museum invited me to think about as I prepared my remarks was to not just give you, some polemic here, but rather to stimulate discussion and give you some conversational tools that you could use when you go amongst your friends and colleagues and amongst your enemies. Friends come and go, but enemies accumulate. You know how that works? So when you visit with your friends, that you could engage them in conversation, not all, where everybody thinks alike, nobody thinks very much. So maybe you could, pose, well, gee, if that's true, but, I heard this, what about this? So here's something, here's a this to think about. So first of all, let's look at the reaction. The reaction involves hydrogen coming into one electrode and oxygen coming into the other electrode, and then hydrogen breaks down a proton and shoots across a membrane, and then recombines with oxygen and makes water vapor. And that sounds so great, and in doing so, it vents electrons through an external circuit. But that reaction is not easy to drive. It requires some assist. It requires a catalyst. And I'm going to go out on a limb here. They said be provocative, and I'm going to be provocative. You know what? Mother Nature is a woman. And you know where a woman goes shopping for a catalyst? She goes to the jewelry store. And guess what the catalyst is? It's platinum. It's platinum. You need platinum electrodes to drive these reactions. So what does that tell you? It tells you that the cost of those electrodes is going to be phenomenal. Have you seen what's happened to the price of platinum over the past 10 years? The demand has gone up, but unlike, people tell me, Don, you've got it so wrong. You remember the first VCR? Remember the Sony Betamax? What did the Sony Betamax sell for? Do you remember? $3,000. It was $29.99. And today you can buy a video cassette recorder for less than $100. That's the economy of scale. This price went from $3,000 down to less than $100. Now, I'm going to ask you something. I'm not an economist. That's not my field. But I know this much. If the world demand for platinum goes from 100 units to 1,000 units, do you think the price of platinum is going to fall? Okay, so cost is an issue. And by the way, the platinum is not immutable. It's not immutable. So what happens over time is that the fuel, that hydrogen fuel that you're feeding in, it's not 100% hydrogen. There are always some impurities. Always impurities. What happens to those impurities? Just as, friends come and go, but enemies accumulate. The hydrogen comes and goes, but the impurities accumulate. And over time, some of the reactive sites on the on the platinum are poisoned. And so then the effectiveness of the catalyst decreases in the same way that the effectiveness of a rechargeable battery decreases over time. There's capacity fade. Everybody who has ever had a cell phone or a laptop computer knows about capacity fade. What people don't know is the same thing afflicts fuel cells. So then you start thinking, well, what's the antidote to capacity fade? You buy a new battery. So think about the economics of buying new fuel cells that have the platinum electrodes. So there's a cost issue. So if I were in charge of the research on fuel cells, there's only one thing I would fund. Only one, because we don't get beyond this. It's a non-starter, and that is non-noble metal catalyst. If we do not get beyond platinum, it's a non-starter. It doesn't matter. So we can't sweep that under the rug. That's got to be in any discussion. Second thing, hydrogen. Where does it come from? The hydrogen tree. It's everywhere. No, it's not. It takes energy to make hydrogen. So what are the conventional means to make hydrogen? Well, there's electrolysis of water. There's water everywhere. So there's hydrogen everywhere. But it takes energy to break that bond. And you don't break that bond with 100% efficiency. So let me see. We're going to break the bond. We're going to take the hydrogen with some inefficiency in this step. We're going to compress it and then take it over here, and then we're going to put it in a vehicle. Then we're going to bleed it across a proton exchange membrane, generate some electricity with some loss of efficiency. Now, where I'm going to be coming from is I'm going to say, why don't we just take that electrical energy, put it into a battery, and short circuit all of this other stuff? So there are some inefficiencies there. Okay, but some people will say, well, we don't have to make hydrogen by electrolyzing water. We can make hydrogen by catalytic cracking of hydrocarbons. Okay? Let's think about that. What does that really mean? What that means is that we find something that consists of hydrogen and carbon. All right? And first of all, it's catalytically cracking. What do you think the composition of the catalyst is going to be? Remember, Mother Nature's in charge here. What do you think that catalyst is made of? It's made of platinum. You're good students. This is a very good student. John, very good students. Okay. It's made of platinum. But the reaction doesn't run at room temperature. What temperature does it run at? It's not running at cryogenic temperatures. It's running at about 300 degrees centigrade. So we got a platinum substrate, 300 degrees centigrade. We're going to put a hydrocarbon in there like methane or something that comes that you can pull up to the gas pump. And you don't want to change your lifestyle at all, right? You want to keep everything the way it is. Squeeze in this hydrocarbon fuel, and then on a car it converts to hydrogen. What do you think happens to the carbon? Has anybody told you what happens to the carbon when you catalytically crack the hydrocarbon? What happens to the carbon? It goes up the stack as CO2. So now you have the hydrocarbon fuel catalytically cracked to make hydrogen, which goes into a device that electrochemically converts the hydrogen just created into electricity to drive an electric motor, and then you vent CO2. So you've invented something called an electric car with a tailpipe. And the amount of carbon that goes up the stack is tantamount to the amount of carbon you'd make if you just took the stuff, the hydrocarbon fuel, and put it into the engine and burned it. What you've done is you've found in a very elaborate way to drive the cost of transportation sky high. So that's another way of making hydrogen. So there's the cost of hydrogen itself. None of these processes are cheap. And there's a huge debate in the field about whether the catalytic cracking of hydrocarbon ought to take place on the vehicle. So now think about this. Somewhere in your car, maybe right underneath your seat, is something running at 300 degrees centigrade and flowing methane over it, converting it to hydrogen. Okay? Somewhere, it's got to be somewhere in a car. No, I don't want it under me. I'll put it underneath the kids in the back seat. That's a better place, right? Who cares? It's the kids, The other place to put it is in the station at the corner. So we'll have tanker trucks, and we'll bring up the hydrocarbon, and then we'll convert it, and we'll have large inventories of hydrogen on the stations. So then that leads me to our third point. So if we have hydrogen coming from the stations, so how do we put it on the car? I mean, we've got natural gas. Have you ever driven around Boston? Have you ever come to these places where it says that no LNG allowed? So if you've got liquefied natural gas, you can't go through the Callahan Tunnel. You can't go through the Sumner Tunnel. So you think if you can't go through with LNG, you can go through with hydrogen? No. So any fool can put hydrogen on a car. You put it in a steel tank, 10,000 psi, you put various regulators on it, and so on. But now let's put it on a car and make the car crash worthy. Okay? That's another issue. So safety is number one. If you're in the auto industry, nothing trumps safety. And putting hydrogen on a car and making that car safe is not a trivial matter. So what am I talking? What's the subtext here? Cost, 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 cost. Remember, I said door number 2 was works at the lab bench but is inviable on economic grounds. And we're not talking about transportation for the few. We're talking about displacing automobiles wholesale. And that's not going to happen unless the cost is right. So hydrogen storage is an issue. And then the last one is, where are you going to buy the stuff? Where are you going to buy the stuff? What can you ship all over this country right now? You can ship gas. Gasoline goes up and down the highways and tanker trucks. You can ship electrons all over the country. But you can't send hydrogen through natural gas pipeline because hydrogen is a tiny molecule. It's not a hydrocarbon, it's just the hydro minus the carbon. It's tiny. Did you see that study that, you remember that NASA study recently that the fellow got his knuckles rapped because he was talking about climate change and well, there's another study. The study was done at Caltech by people who were NASA sponsored. And they basically took the leakage rates of gas from natural gas pipelines and applied that to hydrogen. If there were, at the cost of $20 trillion, an infrastructure to ship hydrogen all over this country, what would be the leakage rate? You know anything about the hydrogen-hydrogen bond with respect to infrared absorption? Is it a good absorber or is it a bad absorber? It's a good absorber. So if you start taking all the hydrogen to be leaking out all these pipelines, in point of fact, the contribution to global warming is this. So, I'm looking at all this going, well, if this is supposed to address the problem of climate change, what? I'm missing something here. The cost is wrong, the technology isn't available, and in the end, there's an MIT study done, not by me, I'm talking about some work that my colleagues did in 2003 that said if you look at all the available alternative technologies for transportation, a hybrid diesel-electric would be superior to any of the other options that are out there. And I don't mean American diesel. I'm talking about advanced European diesel that uses low sulfur fuel, et cetera, et cetera. So if that's there and it's readily available, why aren't we going for it? What are we doing with this other program? The only industry I know of that's exploited fuel cells to any extent is NASA. And the price point, the NASA price point is very different from a General Motors price point. Okay? And you've got to understand that. It's very different. So let's think about batteries. Let's look at batteries. That's where I would put my stock. I said the fuel cell was invented in 1839 by William Grove. And I can't go down the street and buy a fuel cell. I can't go up the street and buy fuel for my fuel cell. Okay. That's 1839. But that's relatively new. The battery, in fact, was invented an entire 39 years earlier by Alessandro Volta. And we know about batteries. But before I talk about batteries, I want to talk about Volta and what the invention of the battery meant. The invention of the battery was a sea change in technology. Because up until that time, if you looked at particular materials technology, where did the origination occur? It didn't occur in academic institutions. It occurred in the field. The blacksmith didn't know about phase transformation kinetics in iron, but the blacksmith knew how to treat the horseshoe to give to it the proper properties. People were glazing pottery going back 3,000 to 4,000 years ago. They didn't know anything about doping with aliovalent ions and silicate networks. That came later. People didn't sit around waiting for some professor to enunciate the 3 laws of thermodynamics, then they went out and invented fire. Happened inverse, didn't it? Happened inverse. But not with electrochemistry. Electrochemistry was different. Electrochemistry began in the late 1700s, 2 places in Italy. First, there was Galvani in Bologna, who was looking at the frog's leg, and he reasoned that electrical impulses could cause mechanical motion. So motion, electrical energy causes mechanical motion. And then Volta subsequently realized that by putting a stack of plates, a pile of plates, silver zinc, separated by cardboard soaked in saline solution, that he could cause a chemical change, corrosion, to exude an electronic current. So now I've got chemical change give me electronic current can give me mechanical motion. Bingo, there it is. He was at the University of Padua. 2 professors, 2 universities, they bring in the era of university research and development. Nobody imagined the professors could do anything of use. These proved differently. So that's 1800. The paper's read at the Royal Society in London. Sir Humphrey Davy has immediately taken these voltaic piles, electric batteries, and applying them to the electrolytic extraction of metals. Go look up who quote-unquote discovered potassium. It's Sir Humphrey Davy. How did he do it? He took Volta's battery and he electrolyzed potassium hydroxide. He made potassium metal. Could have been made before. They start cleaning up the periodic table. People start thinking about electrodeposition, electroforming, electromachining. It took the world by storm. By the time Grove conceived the fuel cell, electrochemical technology was on its way. And it is to this day. So we have the starting lighting ignition battery, lead acid, it's under the hood of the car, 35 watt-hours a kilogram. That's the metric. That's how much energy is in that box there. 35 watt-hours a kilogram. Looking around, I can see a number of people here that remember the 1950s and the old electronic flashes powered by nickel-cadmium batteries, rechargeables. Those were around 45, 55 watt-hours a kilogram. Then came nickel metal hydride batteries, 1990, 90 watt-hours a kilogram, enabled the laptop computer. Everything else was available to make the laptop computer except the battery. If you put a lead-acid battery in a laptop computer in 1990, you would have had either this honking big laptop computer, which would have obviated the need for health clubs, because you would have bought the laptop, you would have bought something to put on your forehead, you would have carried this laptop around. There's this joke, I got to tell you this joke. So the joke is, there's this fellow, he's in the old Soviet Union, and he invents the electric watch. It's a battery joke, so I can be self-deprecating, okay? I have a sense of humor. So he invents an electric watch, and he's going to get the Order of Lenin, so they summon him to Moscow. He comes from Siberia, he takes the train, he gets to Moscow. He's going to go to see the first secretary of the Communist Party. He's going to get the Order of Lenin. So he's waiting in the anteroom, and then finally the assistant of the first secretary comes on. He says, the first secretary is ready to see you. So this fellow bends over, he picks up these two big suitcases, he starts walking. He says, no, leave your baggage out there, just come on in. He says, this is not my bag. He says, these are the batteries. So you need, two big suitcases to power the watch. Yeah, that's the joke. So now, thank you. So how are we going to get beyond this? So we have now the nickel metal hydride battery, which is at about 90 watt-hours a kilogram. So now you have something that you can put on your lap, and it'll run for 3 hours, say. But it's an arms race, because now the functionality of the laptop keeps increasing. You've got more utilities on there. You've got the colored screens. You've got DVD players, et cetera, and all of this is consuming power. So it seems as though batteries haven't improved. But your perceptions are wrong. It's about the woman on the West Coast. You know, you keep looking to the east for the ocean. The batteries are far superior. So lithium ion comes online in about 1995 at about 150 watt-hours a kilogram. And there are some lithium ion packs that are in excess of 200 watt-hours a kilogram. Remember, we're starting with lead acid at 35. And it goes on and on and on. So now where's the limit? You know, on the basis of what I've seen and working with my colleagues at MIT, the ingress of material scientists is raising that ceiling higher and higher. Where does it end? I don't know. As Bohr said, prediction is dangerous when it's about the future. But we're not up against some natural law like the speed of light. So if I could give you a battery today, maybe today is too soon. You need to be a little bit patient. But suppose 2 years from now I could give you a battery that gave you 300 watt-hours a kilogram. 300 watt-hours a kilogram. My rule is 1 watt-hour a kilogram is 1 mile practical driving range. So if I had 200 watt-hours a kilogram in an all-electric vehicle, I could drive 200 miles. And I don't mean with a 90-pound jockey and a car with a drag coefficient of 0.18. I'm talking about, you know, any 4 people in this room get in a car and we drive to New York. If I had 300 watt-hours a kilogram, I could go 300 miles. How many days in your life do you have to drive more than 300 miles? That's different. That changes everything. So why aren't we there? Because we haven't invested money into battery research as we put into some of our other choices, and I'm not going to disparage them, so I refuse to name them, but you know what they are. You know what we spend money on. If we put that kind of money into battery research, be here right now. Huh? It's a resource-limited problem. We choose not to commit the resources, so we've got what we've got. It's just by good grace of whatever's out there that we've got as far as we have. So I'm saying we need to think about this. Make some choices. So I'm going to wrap this up because I don't want to talk too long. I want to get into discussion. So let me end by giving some personal remarks. Okay. So how did I get into this? You know, they asked me, they want to know something about the scientist and so on. I don't know if this is true or not, but that's what they told me. So, all right, so how did I get into this? So I came here in '77. I got on the faculty. I worked for a number of years posturing to get tenure. And yes, you posture. You posture. You pretend to be very intellectual, and you publish in scholarly journals, and you do everything except engineering, okay? And so then finally I got tenure, and then I said, okay, that's done. Tenure means never having to say you're sorry. So now, what are we going to do? So you turn around and you say, what are the important problems facing the world, and what am I going to do about them? So, you know, given my skills, I mean, obviously I'm not fit to work in molecular biology. Okay, that's not my technical center of gravity. So I looked around and started looking at the issues associated with electrochemistry, electrochemical generation of metals, and then ultimately electrochemical generation of energy and the storage of sane. So, and it's been fun. It's been a lot of fun. It's been a lot of fun. So I urge the young people in the audience to think about careers in science and engineering that have an impact on the world around us. Because, you know, as far as I'm concerned, the number one problem facing us is global climate change. Global climate change. It's important. It's not urgent. If you go out there tonight, you won't know it. You won't know it next week or next week. Huh? But let's think about legacy. Let's think about legacy. Huh? And we know enough now that it's time we started doing something about it. And so I think it's important that because we know, we need to act. We need to act. We need to act responsibly. And we shouldn't be putting all our eggs in one basket. I don't want you to think that what I'm saying is that we shouldn't be looking at fuel cells. But when the kids are small, you ever go watch them play soccer? What do you see? You see the ball is here and two teams following the ball like this. So what do you do about this? You say, well, you know, maybe we could fan out. You know, maybe the ball's liable to go over there. Isn't that what Gretzky said? So most people go where the puck is. I go where the puck will be next. Okay. So what do? I have to anticipate. Huh? So let's encourage people to distribute the resources and work on a plurality of options, and let's solve this problem. And if you read the article yesterday, you know that I was affected by the 60s. Even though I was in Canada, I was affected by the 60s. And so one of the... that was very nice. This sort of very understatement, litotes. So, you know, there's the you know, Lee Iacocca says, lead follower, get off the road, right? But Stokely Carmichael said, if you're not part of the solution, you're part of the problem, right? So, and then if I can hearken to my Ukrainian heritage, there was a Ukrainian writer at the turn of the century, Ivan Franko, who said, make sure that the monument that your children erect in your memory isn't made of the stones that people threw at you for your misdeeds. That's better than lead follower, get off the road, isn't it? A little bit. Okay, let's break into discussion.
Thank you very much indeed. I told you he came highly recommended. Now, you know what happens next. Spontaneous self-assembly. We've got no more than 10 minutes, and we want to hear back from you after that as to which of the issues that you've heard about or which particular questions about those issues you'd like to discuss with Don Sadoway for the rest of the evening. So please, go to it. Thank you. That was great. Okay. Could you post up the top one? I'm just going to read a few of these questions, and then we'll see how we want to do this. The first of the questions that came in was if the US is not investing in battery research and development, and the implications of what our speaker was saying were that I think the US is not investing that much. Are other countries doing that? So how is international investment in this area? Why isn't the US investing in battery R&D? That's a related question, I think. One from a person with some technical knowledge here. What about capacitors? What are the ecological and economic costs of lithium batteries for cars? And are batteries also the answer for developing countries like China and India, as well as highly industrialized countries? I mean, China increasingly industrialized anyway, but is this a solution potentially for transport worldwide? There's a good start there. Don, would you like to get into this question of levels of investment in the US? Why isn't it greater than it is, do you think?
Okay. Well, you know, there's different sources of investment. There's government funded investment in R&D, and then there's private sources of investment. And when it comes to private sources of investment, they need no government guidance. They know where the money is to be made. So if you start looking at price points for the use of batteries, when you buy a battery for your laptop computer, you're probably paying between $5,000 and $10,000 a kilowatt hour. You can do the math. You know how much you paid. You paid, say, $100, $200 or whatever it was for the replacement battery. Flip it over. It'll tell you how many milliamp hours it runs, and its voltage is, round numbers, about 4 volts. It's a lithium cell. It's about 3.6, but use 4. And do the math, and you'll find that you're paying about $10,000 a kilowatt hour to buy a battery for your laptop. For cell phones, it's probably closer to $1,000 a kilowatt hour. Guess what the price point is for automotive traction? $100 a kilowatt hour. So where do you think people are going to be doing their research and development? They're going to be focused on computer batteries, these things that, you know, toys. And people spend all kinds of money on, you know, goofy stuff like the iPod and stuff like that. They, you know, portable music, portable entertainment. You know. So there needs to be no guidance there. But when it comes to something like how are you going to get down to $100 a kilowatt hour, it's, you know, lithium ion's got cobalt in the cathode. Cobalt's expensive. And again, you know, if you think you increase the world demand by a factor of 10, the price of cobalt's going to go down, I think you're dreaming. You're dreaming. So that's where the role of government is. It's in looking at the common good. We don't need the government to help us figure out how to make better entertainment tools, I would hope. So who's funding that kind of research? And it's not here in the United States. Not here in the United States. I think by and large people have stepped back and basically have said that it's going to be in the domain of the market-driven applications. And so the hope is that if we get really, really good at making laptop batteries, eventually they'll trickle down and end up in hybrids and so on. And you see some evidence of that. I mean, some of the car companies are trying to do this, but it's a very different kind of engineering application.
I don't particularly want to drive the conversation in a political direction. On the other hand, I'm not frightened of it. But we recently had a State of the Union address in which the President was saying America had to reduce its dependence, I think, on foreign oil. That seems to be part of, I'm getting feedback, I'll move from here. That seems to be part of the picture you're painting. Do you think then that the prospects in the future might be a bit better for getting government support for this kind of research? Are you hopeful as a result of the State of the Union address or not?
If I took the words of the State of the Union address and I tried to apply them into action in the funding arena, the answer is yes. So let's wait and see.
Okay.
I think that what was it? The Roman poet, politician Juvenal said that men need not so much be informed as be reminded. So let me remind you of a fact. The United States, from 1975 to 1982, reduced its dependence on Middle Eastern imported oil by how much? 5%, 10%, 20%, 30%, 50%, 70%, 87%. 87%. It went almost to zero. So don't look at me and say, well, I mean, that's absurd. It can't be done. It almost was done after the 73 oil shock.
Right.
And what happens when this country decreases its dependence on imported oil by 87% from a particular region? Guess what happens to the price? It falls dramatically. And then we go back and buy the stuff, and then we're back into the soup again. Instead, we need to go all the way and say, you can give it to us for free. We don't want it, don't need it, keep it. I could say something else, but it's being filmed. There's another verb, transitive verb. Okay, let's...
Now we've got it. Just before we do that, there's at least one comment from the audience here.
Get rid of our Middle East oil source. How does batteries help us here? We still have to make the power from something. Oil is still the
Just a sec.
way to make it.
Say that again into a mic.
If we get rid of our Middle East power source, power dependency on the Middle East oil, we still have to make the power from something. All the mechanisms we're talking about are just transport mechanisms. Hydrogen, batteries, even gasoline is just a good transport mechanism. It still has to come from someplace, and Middle East oil is always going to be one competitive source.
Try uranium.
Okay, so there, what are the sources of electricity? I didn't talk about that in my remarks because that's not part of my research, but I'll venture there and would do so if asked to by the audience. So let's think about where do electrons come from? They don't grow on the electron tree either. Right? So where do they come from? Well, in this country, 75% of them come from burning fossil fuel. Okay? About 55% of them come from burning coal. And coal is a fossil fuel, to be sure, but you know what? We burn coal, we burn American coal. So that's point number one. And then you got to bridge. We got to have the courage of our convictions. We cannot say we want no greenhouse gases, we know no imported oil, we want to keep our style of living unaltered, maybe even enhanced, but we're going to say no to nuclear, we're going to say no to some of these other options. All of you here who are embracing solar, you embrace nuclear. Because how do you think the sun generates its energy? The sun is the biggest nuclear reactor in your life. It's nuclear fusion. So why don't we do something that is, solo-mimetic? It's 93 million miles away, and
It's quite hot, though.
and it's arriving daily.
Yes.
So my point is that, make me czar for a day, give me the resources. Where would I put them? I'd put them into, let's redouble our efforts on fusion. Why has fusion not been successful? Because the people working on it are stupid? Or maybe because they've been under-resourced? So let's imagine the future that's carbon-free, and let's commit the resources to get there. And yes, nuclear maybe has to be in that mix. But certainly initially we've got domestic supplies of coal. There's natural gas in Canada. But let's move quickly to get out of the dependence on non-renewables. And biomass, it's in the mix. It's going to give us maybe 5%, but 5% is still 5%. Let's look at wind. Let's look at solar, by all means. If anybody in this room thinks that the answer to our energy problem can fit on a bumper sticker, you're wrong. There's no relativism here. I'm going to tell you to your face, you're wrong. It's a complex problem, and it requires an elaborate solution. And when we become intolerant of a plurality of approaches, all we're doing is just playing into the hands of people who want to keep selling us this black goo. So think about it.
Okay,
Somebody wants to
just a
just come
comment
back with the
on fusion. We've been working on fusion for 40 years. We haven't gone anywhere. One comment is you have to keep it together, and we don't have a gravitational field like in the sun to just keep that hydrogen there.
We've been working on fuel cells since 1839, and we don't have a gravitational field either. My point is that those kinds of arguments don't really, I'm sorry. I mean, if I showed you the very first transistor, this piece of germanium about the size of my fist, with a couple of wires coming in on the back, and I said to you on December 23rd, 1947, someday you'll find 16 million of these on a piece of real estate the size of my fingernail, you'd say you're crazy. So, I mean, I respect what you're saying, but please, let's not make that the pretense for the future.
There's a comment just in the middle of the room here. Please.
Sir, don't mean to presume, don't know that much about your subject area, but I've read Michael, what was his name, Richard Rhodes's book about the making of the hydrogen bomb. To make a hydrogen bomb, a 10-story high steel welded container had to be built to contain the deuterium reaction that would then create all of the elements of the universe and give a microscopic version of the Big Bang in order to make the hydrogen bomb using an atomic bomb as the fuse. That's what I understood from the book I read about this. I don't find that feasible on Earth. I respect the fact that the nuclear fusion argument is getting into the environmental colloquy, but I personally think that it was always wrong that when the physicists who were considered the best natural philosophers of their age and the most intelligent people came up with the atomic bomb, they essentially contradicted all of the natural philosophy by creating a baby star on the face of a planet. Anything along those lines, sir, I don't think is feasible in terms of the continuation of the human species.
Okay, thank you. That's very clear. Would you like to respond to that?
Yeah, I think that saying that nuclear power is the same reaction, nuclear fusion is the same reaction as in the hydrogen bomb is really saying that all females are queens, right?
I don't understand that statement.
No, I'm going to explain it. So that it's true that there is one type of reaction that follows the hydrogen bomb trajectory, but I'm talking about benign reactions that generate energy and are not, pardon? Well, I mean, if I knew the answer to that, I wouldn't be standing here. I'd be lying my back on a kidney-shaped pool where the sun always shines. So, I mean, this is, you're asking me to tell you how to make, yes, you are. You're saying that because it can't be done, or the only time that it could be done, it leads to mass destruction. I mean, these are defeatist arguments, and I won't entertain them. I'm sorry. We disagree. This is tantamount to saying that if I look at the Darlington nuclear power plant that I grew up next against, that's tantamount to a nuclear bomb, and it isn't.
Okay.
It doesn't. It doesn't. It doesn't. Well, you just said if it gets out of control. I mean, what happens if your gasoline tank explodes? I mean, you know, I'm sorry, but...
Okay, we've got a disagreement there, and people are allowed to disagree. It's okay. Can I just...
I know I'm in Cambridge, but I feel that I'm free to disagree.
You are free to disagree. Can we... Oh,
Thank you for the question, though. I mean,
can we go back to some of the questions at the bottom of the last slide? We had this rather cryptic question, to me at least. What about capacitors? Who asked that, please? Would you like just to say another sentence about that? And then Don could come back and comment.
Why don't I generalize the question to say, what do you consider to be the best way of storing electrical energy for propulsion? Since that wants to be want to be limited to that for right now. I asked, what about capacitors? I think I know the answer. What about flywheels, et cetera, et cetera? I want you to think big thoughts, maybe beyond your field. If you think there's anything out there that at least might in the future be an answer. Thank you.
yeah, I think capacitors have a role to play. I think that it's part of the whole theme about it doesn't fit on a bumper sticker. And so, you know, when I talk about an electric vehicle, it means it has an electric motor. But, you know, even people who are committed to a fuel cell powered vehicle are going to need to have a battery on there because, you know, wasn't that long ago, you woke up in the morning, it was about 10 degrees Fahrenheit outside. Guess what? Your fuel cell doesn't work when it's 10 degrees Fahrenheit. So how are you going to get moving? You're going to need a battery until that fuel cell gets up to temperature. And a capacitor has a role to play. Capacitors can take charge very quickly and they can give back charge very quickly. Nothing can compete with a capacitor when it comes to charge and discharge rate. But capacitors don't have enormous capacity. The good news is you can put charge on them quickly, but you can't put a lot of charge on them. So capacitors would figure into a power scheme. And the other thing about capacitors is that they tend to leak. A high energy capacitor, so again, if I had the resources, I would put money into exploring advanced materials for superior capacitors. And ultimately, what we're really talking about here is advanced materials. I'm not a battery guy, I'm a materials guy. And if we don't have advanced materials, you know, we can only do so much with the things that we've got. Engineering will get you so far, but a new material that can store more charge would be very, very useful. So I see capacitors in the mix, but I see capacitors as playing a role in sort of an energy boost, perhaps on acceleration, but you're not going to go from here to New York on capacitive charge.
Excuse me.
Let me see.
I also asked about capacitors, but my handwriting was not very clear.
Okay.
Now, I was specifically interested in, I think both this month in Scientific American and also out of MIT, they've talked about nanotechnology for capacitors. And since capacitors go like 1/d, why, that sounds like a really good idea. Related to that, however, is what sort of energy densities or total energy stored in a car do we begin to get worried about when it short circuits? And did we just make a bomb there? Thank you.
Okay, so let's talk about the capacitors and nanotechnology. I mean, certainly if you resort to more and more interface per unit volume, you'll be able to store more and more charge. So, I mean, that's axiomatic. But again, even allowing for the go down to nanoscopic dimensions, the total amount of charge is just not going to get you very, very far. All right? It'll give you a good boost, and we ought to think about it in those terms. I don't want to dismiss the capacitor, but I don't want to come up here and say, well, fuel cells, I've told you why fuel cells can't work, and then I'll say, but capacitors, that might be the answer. I don't think. I think we got to put that into the mix. As far as bombs go, please don't think about batteries as bombs. I mean, that's just it's inaccurate. The worst thing that you can imagine happening in a battery is a short circuit, and a short circuit could lead to a very, very high rise in the rate of current through a load, and leads to heating, sort of the way your toaster oven works. And the battery could heat up, and it could burst its case. And some of the things that we're working on at MIT involve using components that, when they are exposed to ultra-high temperatures, they won't generate explosions. They won't burst in a flame, but rather they'll just sort of they'll melt down, and that's the end of the story. In other words, they act as a chemical fuse, so that when the temperature gets high enough, the battery essentially takes itself out of existence. So it acts as a fuse to save the surrounding environment. But you know, let's think about this thing from a chemical standpoint. The battery is ultimately a current source that takes chemical energy and converts it into electrical energy. So I want a battery that can give me very, very high levels of electrical energy. And specifically, I want very, very high electric current. Now, how can I, in a one breath, say, I'm going to get very, very high current out of this battery, but the constituents of the battery are going to be benign? They don't, I mean, heck, if we mix them, they won't react. That's a non sequitur. The reason you get high current out of the battery, if you put these two constituents together, they react violently. And we're exploiting that desire for the violent reaction to give us a high current. So when people say, I want to get high current, I want high efficiency, and I want this thing to be environmentally benign so my kid can play with it in the sandbox and put it in her mouth, I'm saying, what are you talking about? It can't be all of these things. And yet, you know, when I look at gasoline, there's no such high standard applied to gasoline. I've never heard people talk to me about, but you know, have you ever seen gasoline explode? Have you ever seen gasoline burst into flame? And I'm going, yeah, we probably shouldn't be putting that in our cars and driving around with our kids in the backseat right over the gas tank. You'll accept that, won't you? But you look for some, you know, and what happens if this car jumps over here and then there's this guy and he happens to be doing this and somebody else reaches into the car and shorts it, and what about that, Sadoway? And I'll go, yeah, you're probably going to have a bad day at the office if that happens, but you know, come on.
My Prius is full of warnings.
Yeah, well, you know, but you know, there is an issue. There is an issue, and that is, you know, if you've got a car and it's got a honking big battery in it and you're in a collision, and you're lying there, and the EMTs show up, and they're going, can we touch the chassis? Because it's electrified. Duh, it's an electric car. Well, is there an answer to that question? Let's think about it. I bet you there are people in this room who can figure out how we can probably get you out of your bashed up Prius as you're lying there, life slipping away. How are we going to do that? What are we going to do?
Ground the car, yeah.
Rubber gloves. What about that? Well, what about something else? Why are they building the Prius with a steel chassis? What if they build it with a fiberglass body?
You've reduced them to size.
Well, fiberglass cracks. Of course it cracks. And you know what else happens? All kinds of bad things happen. But all I'm telling you is there's an answer to this question. It's not that, you know, hell, you know, we ought to just get in the car. We ought to just connect the electrodes to our bodies and gun it, you know, because it's all over. There's no point. Let's just buy the oil and be done with it. There's no point.
Now this, please, person in the back.
I would selfishly ask you if you wouldn't mind moving on to the question about how appropriate this technology is, in your opinion, for developing countries that are seen as part of the tensions around these issues of global warming. In fact, I think I almost heard you say, when you say the big problem is climate change, you almost said China, I think, by inadvertently. So is this just as appropriate and applicable in China and India as it is in the United States and Europe?
Absolutely. I mean, if you take a look at greenhouse gas emissions as a function of gross domestic product, it's essentially linear. And up to a certain point, it reaches a maximum, and then it tails off. So the so-called developed economies are now at a point where they're developing at a rate that doesn't increase greenhouse gas emissions. So it's a really difficult issue in terms of, so that now that we've developed technologies that allow us to put more cars on the road with less greenhouse gas emissions per unit, for us to then preach to the developing world saying, we don't want you to go through the same growth curve, you know, they can look at us and say, what are you talking about? No? So absolutely, what we need to do is to get these technologies out there and make them affordable so that these other countries can enjoy the economic growth without having to go through that maximum, cut that hump off, and move in an environmentally more conservative manner. So again, it's all about finding realistic solutions, practical solutions that are cost effective, not just for this country. And that's why I'm so what's the word? That's why I feel compelled to raise questions about the present trajectory in fuel cells, because if we can't afford it with the platinum and with the lack of the hydrogen infrastructure, how do we expect China and India to be able to afford it? And you know, we really want to get this technology out there and available for everybody. It's, you know, because let's face it, you know, let's think about it. If you drive up and down the highway, which are the cars that are most polluting? They're the old cars. Right? Old cars pollute more than new cars. And who drives old cars and who drives new cars? New cars are driven by people of means. So if we then take the new cars that have the most advanced technology and replace them with cars that have even still more advanced technology and leave the old cars out there, because who drives old cars? People who can't afford new cars. What's our impact on air quality? What we need to do, instead of mandating all of these silly rules, is drive up and down the highway, pull every old clunker over, hand the driver a voucher for $15,000 and say, go to the Toyota store and buy yourself a new car. That'll have an immediate impact on urban air quality. Instead of waiting until some technology comes down the road and people who are already driving late model fuel efficient cars with low emissions, replace them with cars that are infinitesimally better.
Jim, I can't. Don, I'm sorry. I was thinking about something that Jim Hansen was reported as saying. You referred to scientists who had gotten into trouble saying politically unpopular things. But one of the things he was saying as a global warming expert was, we don't have much time. We have to act now. And I'm listening to you very persuasively arguing the case for new research and development to create new generations of more efficient, more powerful batteries. And I'm struck by the question, have we got, how much of a window do we have here to improve our transportation technologies enough to prevent ourselves causing most of the problems we're trying to avoid anyway?
Well, I can't answer the question about how much time we have, because I'm not a climate scientist.
But do you worry about that?
Sure, I worry about it, but I'm not going to, you know, even though I'm an MIT professor, there's certain things I don't know, and I'm going to admit it in front of this audience. So I mean, write that down, all right? But here's something to think about. It's that it's not all or nothing. In other words, it's not that, well, we'll work until finally we've got the battery, and then at midnight, December 31st, some year, we all go to an electric world. I mean, what is the average distance a UPS truck drives in the Boston area per day? 40 miles. 40 miles. You could take a UPS truck today with lead-acid technology today, the lowest, 35 watt-hours a kilogram. What's the Sadoway rule? 1 watt-hour a kilogram, 1 mile. Well, gee, when I went to school, 35 watt-hours a kilogram, that's 35 miles. And that whole fleet of trucks will be driving all over the Boston area with 0 emissions.
What about the lead and the lead batteries when it's still?
Well, we can talk about the lead. I'm talking about tailpipe emissions. We're talking about urban air quality, and we can look at the cost. I'm simply saying I'm not dismissing. The question was, what about the lead that came from the smelter when they made the lead acid battery? No question, except that 99% of the lead from lead acid batteries is recycled, and so there's a fair bit of lead in the system. So, but I know you meant the question honestly, but I don't want people to say, he's right, we better not use lead acid batteries. Okay? We better not use fission or fusion. We better not use this. Well, let's just go and buy some more oil. I'm saying let's use this as an example of how we can put an all-electric fleet into the market. The personal vehicle is going to be one of the last places that we deploy electrics and fuel cells. What are the demonstration vehicles that you know about that fuel cells have been deployed in? They're buses, aren't they? They're not personal care vehicles. I mean, they put one in front of the Congress, but that thing cost half $500,000. You want to pay the Ferrari price to get something that can't outperform a Toyota Corolla? I don't. That's stupid, because you can't drive it anywhere because you can't buy any fuel. So let's think about ways of getting some experience with these vehicles. So let's look for the low-hanging fruit. So I would say let's start introducing them instead of saying, well, we've got, let's see, if I knew the answer to your question, John, and I could say we have 14.5 years, I tell everybody, go home tonight, tell your children we've got 14.5 years. That's it. So I don't want to
Professor Sadoway, we've got a question over on your left.
Are you over there? We've also got someone over here waiting for a question, so let's make sure both get a chance. Yeah.
Yes. Well, I totally agree with you that we need more research in battery technology, but I'm sure that if we go to another university somewhere or an institution, they would also tell us what they need and what they think is a bigger priority. I think, though, we should watch out and be very wary of getting paralysis by analysis. We can overdo the analysis so much that we end up doing nothing, or we feud among which renewable technologies is best. In fact, the electric car is already here. The Prius in Japan has an option button to go all electric. They don't need any gas at all. Why don't we have it in the United States as an option? I'm sure there's certain interests that made sure we didn't have that option. The other thing is there is already a strategy out there by a number of people, and you probably know about the Rocky Mountain Institute, Emory Lovins, and the book or the recent study called the Ending the Oil Game, the End of the Oil Game. Mm-hmm. All those technologies that you talk about are part of that, and what their main compelling idea is that all this business about money, everybody says it's too expensive. You need to just sit down and say, how much will we spend in the next 25 years on oil? And how much would we need to transit from where we are now to a better world in 25 years? And it turns out that it's not a whole lot different. So I think any way we can get in the way of more independence and less fossil fuels is the way to go, but it has to be a combination.
Okay, thank you. Before I ask Don to respond to that, I want to just let our other questioner here say what you would, and then perhaps our speaker could reply to both, and that might, I'm afraid, be the last exchange we have. Please.
What I was going to say is, in the spirit of multiple solutions to these problems, what is your opinion about, and you're talking about urban air quality. You keep mentioning urban air quality. I imagine Cambridge as a place that would be, and Boston too, so bike friendly. And if it were more bike friendly, say like Copenhagen or Amsterdam, there's no hills. We all go really short distances. People use their car to drive, 10 blocks to go to Star Market. What a difference would that make in terms of reduction, only in terms of reduction of pollutants? Okay, so these are two very...
Yes.
John, you've asked me to just put the answers, and I say, I think you're both right. You're both brilliant, but it's not so simple. Absolutely, I believe in a plurality of solutions, and to the extent that we can get people to get out of their cars, we should do so. But I think, you know, that Americans want their cars. They want to get in their cars and go places. And, you know, when they want to do so, I think we need to think about ways of allowing them to do so that don't consume so much hydrocarbon fuel. So I think we want to work on both paths. And I love to get on in rapid transit and so on. And to the extent that that can be part of the solution for urban air quality, it ought to be there.
I just want to comment, my Prius has that button, so when I run out of gas, I go battery only.
Well, that was the gist of what I thought the person who was speaking, unfortunately, through the robot, was saying, that maybe there's more of these technologies available for us to help in the direction you're talking about than we are sometimes inclined to think.
Well, I think that the comment that was made is an indication of what I was saying a little bit earlier about it's not all or nothing. So the hybrid electric is a really good starting point because it takes an electric boost and puts it with a much smaller engine in a sensible hybrid. There are some hybrids out there that are obscene. You know, a V8 hybrid is an oxymoron of epic proportions. All right, this is a feel-good for somebody who's got more money than brains. I just cannot believe this thing. Okay, so you know what you should have is something. It takes about 10 horsepower to take 2,000 pounds with a drag coefficient of about 0.3 and send it down a highway at 60 miles an hour. That's about 2 lawn boys, okay? So you put 2 of those together, and, you know, rule of thumb, if I had a 10 horsepower engine versus a 100 horsepower engine, all things being equal, I probably cut my emissions by a factor of 10. And then when I need to accelerate so I can get up to the end of the access ramp without getting killed, I use the battery boost. And that's the way it should have been designed initially. The Prius, in my opinion, gives really lousy gas mileage to what it should. That car should be getting 75 to 90 miles to the gallon. When people tell me, I got 50 miles a gallon, I'm going, that's it? But that's another conversation. So what's happening is the batteries get better. People can start using the battery for, pardon me. Sorry. The only thing I have is white wine, so I have to clear my throat. Take this off. Edit this out. It's MIT, you know. All right, so as the battery gets stronger, you can start going for greater distances on the battery. And incrementally, the battery, the hybrid will eventually morph into an all-electric. So that's the sort of the subterfuge that we need to encourage. Because otherwise, if you say all electrics, people, you know, all of a sudden there's alarm bells go off. So I'm very happy with the hybrids, and I think that the direction that they're going is advantageous in so far as they make sensible use of the internal combustion engine. But when you put a honking big internal combustion engine, and all you do is you kill power when you come to a stop sign. I mean, that's really, it's nuts. It's just nuts.
Well, I wish we could go on, and we clearly could, but we'd be taking liberties with your time and more particularly with Professor Sadoway's time. I want to just make a couple of comments before I close by thanking our speaker. The first one is that all of the questions, and we didn't get a chance to discuss them all the questions that were sent in or fed back will be going online overnight, and you can carry on this conversation online tomorrow. And judging by the kinds of comments that have been made, it looks as if many of you would like to do that, so please do that. The other comment I thought I'd make, just looking ahead, apart from telling you, again, please leave your email address with us so we can contact you about next month and the month after, but I just thought I'd encourage those of you who maybe didn't have the best angles of view or didn't have the most comfortable position in the room tonight. In about a year from now, all being well, we hope to be running these Soapbox events in an expanded MIT museum on the ground floor right off Mass Ave in a rather more comfortable environment. So watch this space and keep your fingers crossed. That's by way of the announcements. You wouldn't want us to finish, though, without thanking our speaker. He was rather good, wasn't he? Thank you very much. Thank you. Thank you. Thanks for all your support, and hope to see you again here soon. Thank you. Thanks a lot.
What about the slim cell battery?